Today we move forward to Chapter 2. And I created a handout because in Chapter 2, this first section, there's a lot of theorems that we're going to go through. You don't need to write all these theorems down. You don't need to memorize them. We're going to get to the point where we learn how to use them, and that will be the important thing. All right, so the first thing we have in Chapter 2 is a definition. In Chapter 2, we are going to deal with second-order differential equations. And what makes an equation a second-order differential equation? It has a second derivative, that's correct, y double prime. So we're going to talk about non-homogeneous linear equations and their associated homogeneous linear equations. The word homogeneous in Chapter 2 does not mean the same thing as the word homogeneous meant in Chapter 1. In Chapter 1, homogeneous meant
Same power.
every term had the same power. In Chapter 2, we're going to use the definition that many of you have seen in linear algebra. Homogeneous means equal to 0. So this is what the associated homogeneous equation is. It's the exact same equation except it's equal 0 instead of equal to some function f of x. Now we call these equations linear. And again, linear in Chapter 2 does not mean the same thing as a linear equation in Chapter 1. What do we mean by linear in general in a math class?
Everything's the first power.
Everything has first power. Okay, and when we say linear in this situation, what we mean is all the y's are to the first power. So for example, if I were to have this exact same equation, but I had a y prime squared, that would no longer be considered a linear second order differential equation.
Actually, so if homogeneous means equal to 0, that means exact equations are homogeneous because they're equal to 0.
Exact equations don't always have to be equal to 0.
Okay.
They're quite often written that way, but they're not always equal to 0. And you got to be careful there because you're using the word homogeneous in two different ways.
Mm-hmm.
So yeah, you could say an exact equation is written in a form that is homogeneous, but that would be confusing because in that chapter, homogeneous meant something else. Okay. All right, so when we talk about linear second-order equations, we mean that none of the y's, the y double primes, or the y double primes have any exponents on them. The x's, these functions here, a of x, b of x, c of x, these may have x squared, square root of x, sine x. They can have anything you want. When we say linear, we're talking about the y's are linear. No exponents on the y's, no dividing by y's, that sort of thing. All right, so an example might be, why do we study second-order differential equations? An example might be spring motion. Suppose that a mass m is attached to both a spring that exerts a force F sub s and to a dash pot that exerts a force F sub r on the mass. What is a dash pot? It's a nice new word. Anybody ever heard of a dash pot before?
Or the desktop.
That's something else.
It's like a spring loaded.
No. A dash pot generally is like a shock absorber. What's a shock absorber?
White pad, some sort.
Takes the force of
It's rubber.
another barrel, whatever.
It takes the force of the projectile. So in your car has springs which bounce up and down so the ride feels smoother, but it also has shock absorbers, or more likely struts if it's a newer car. And what the shock absorbers do is they keep your car from bouncing up and down forever every time you hit a bump. So the springs make your car dip and rise, which makes the ride more comfortable, but then the shock absorber, or the dash pot, stops the car from keeping the bounce forever. And you don't want your car bouncing forever because it would bounce up and down and it would get higher and higher and you'd start to lose traction and it would be very uncomfortable.
How do you throw up in the process?
You would probably throw up eventually if you maintain contact with the road and stay on the road. So, okay. So, we're going to assume that the restoring force F sub s of the spring is proportional to the displacement y of the mass from its equilibrium position. And in which case you get force equals minus ky. That's a famous one. Anybody know that one? Named after some famous guy?
Newton.
Not Newton. Good guess, though. That's called Hooke's law.
Oh yeah.
How many laws does Hooke have? He has this one. I don't know how many laws he has in general, but this one says force is proportional to the distance that you've stretched or compressed the spring. That's Hooke's law.
Usually it's
Okay, we assume that the dash pot force is proportional to the velocity. So the force from the dash pot depends on how fast the thing is going. The faster it's going, the more force it gives. So the force is proportional to the velocity, which is, of course, proportional to the derivative of position. Velocity is derivative of position. All right, so in the end, now we go talk to Newton. Newton says, of course, that mass times acceleration equals force. And we have two forces. We have the dash pot force and the spring force. The spring force was a multiple of the first derivative, and the resistance force was a multiple of the distance. And acceleration, of course, is second derivative. So this is an example of where we end up with a second order differential equation, where we have both second derivative and first derivative showing up in the same equation. And this would be a homogeneous equation. This would assume that there's no outside force working on the spring. If you have an outside force working on the spring, then you would have what we call forced motion, and you would have a force over here. Why might you want an outside force working on your spring? The outside force might be friction, which could be slowing you down more. Quite often, friction is taken care of as part of the dash pot resistance, though. So this is usually a different external force. What other kind of external force might you want on your spring? Well, if you've got something bouncing up and down, and you want it to stay bouncing up and down, what do you have to do? You have to add a force, because otherwise friction and wind resistance and all those other things are going to make it stop. So, for example, clocks generally run on a spring system. So that's why you have to put a battery in them. The battery provides the force, which keeps the clock running. All right, so now we're going to have a whole bunch of theorems. And then when we get done with these whole bunch of theorems, we'll see how this stuff actually works. So the first theorem says, let y1 and y2 be any two solutions of a homogeneous second order linear equation on some interval I. Let C1 and C2 be any constants in the world. Then y equals C1y1 plus C2y2 is also a solution to the equation on the interval. So what does that say? That says if you have two solutions, what can you do? Multiply by a constant, add them together, and what do you get? You get yet another solution. You get a third solution. So once you have two solutions, you can make a third solution. And then once you have three solutions, what could you do? Make another one. And so once you have two solutions, how many answers do you really have? You really have an infinite number of solutions once you have two. All right, this one's a very easy one to prove, so let's prove it. Our differential equation is going to be a y double prime plus by prime plus cy equals 0. Equals 0 because it did tell us that this differential equation was homogeneous. And we know that y1 and y2 are solutions. So what does it mean to say y1 and y2 are solutions? They satisfy. So if I take y1 and I take its derivative and I take its second derivative and I plug all that stuff in, it'll all cancel out and I'll get 0. That's what it means for a y1 to be a solution. All right, so let's let y equal this c1y1 plus c2y2. I want to prove that this equation is a solution to that differential equation. So what I need to do is I need to take the derivative, I need to take the second derivative, I need to plug it all in and show that it adds up to 0. So y prime is, what's the derivative of c1y1 plus c2y2? c1 plus c2?
Yeah.
Close.
Plus C. Plus C.
That's integral.
That would be integral.
Sorry.
What's the derivative of y1? It's y1 prime. It's dy dx. It doesn't just disappear. We're not doing the derivative of y1 with respect to y1. So this is actually going to be c1 y1 prime plus c2 y2 prime. How come I didn't have to use product rule there? I'm multiplying things together, c1 times y1. C is a constant. That's why I don't need product rule. And y double prime. By the same reasoning, it's going to be c1 y1 double prime plus c2 y2 double prime. I'm going to take all this stuff. I'm going to take y, I'm going to take y prime, I'm going to take y double prime, and I'm going to plug it all into that equation. I get A times c1 y1 double prime plus c2 y2 double prime plus B times the derivative, which is c1 y1 prime plus c2 y2 prime plus C times the original function, which was c1 y1 plus c2 y2. And now I need to convince you that that's the number 0. You convinced me. Oh, very good. How did I do that? Oh, that's a foolish reason.
Works for me.
Works for you? All right, well, I'm going to use the distributive property. Then I'm going to use the commutative property. And I'm going to rewrite this whole thing. I'm going to write this as A C1 Y1 double prime plus B C1 Y1 prime plus C C1 Y1. And then similarly plus A C2 Y2 double prime plus B C2 Y2 prime plus C C2 Y2. So what did I do there?
Distributed.
I distributed the A, the B, the C through, and then I changed the order. I grouped them together so that I put all the Y1 things together and all the Y2 things together. Why does that help? I can now pull C1 out of this first group. And when I pull C1 out, I'm left with A Y1 double prime plus B Y1 prime plus C Y1 prime. Or Y1, I mean. What can you tell me about that? That's the number. That's the number 0. Why is that equal to 0? Because we stated that Y1 was the solution to this equation. So this is, I factor the C1 out, and what's left is the number 0.
Wait, can you repeat that again? Like, why is that?
When I pull the number C1 out, I'm left with A Y1 double prime plus B Y1 prime plus C Y1. But remember, Y1 is an answer to this equation, which means when I put Y1 there, Y1 prime there, Y1 double prime there, I get 0. Because it satisfies that equation. That was our hypothesis. Plus, I do the same thing here. I pull out the C2. Our hypothesis is also that Y2 is an answer. So when I pull Y2 out, I get 0 there. And so I have 0 plus 0, which is 0. So once you have any two solutions, you can make yourself a third one by multiplying the first one by any number, multiply the second one by any number, and add them together. So once you have any two solutions, you actually have an infinite number of solutions. Questions on that? All right, moving on. This one says, suppose that the functions p, q, and f are all continuous on the open interval I, containing some point a. Then, given any two numbers, b0 and b1, the second order differential equation y double prime plus p of x y prime plus q of x y equals f of x has a unique solution on the entire interval I that satisfies the initial conditions. All right, I'm not going to prove this theorem because this one's a lot harder to prove. They don't even prove it in your book. Oh, you can't even see that, can you? There we go. Well, it's on your piece of paper too. So, what does this theorem do for us?
Does that say that that form only has one solution? Or it has a unique solution like the two?
It says if I give you two initial conditions, one involving the function and one involving the derivative, how many answers do you get?
One.
You're guaranteed to get exactly one answer.
Unique.
Unique answer.
So
One,
y-
exactly
Is it
one.
y equals something, or is it y1 equals this, y2 equals that?
The answer you would get would be y equals some function. That's always our goal in differential equations. Our goal is always to get the original function back. Once we know the original function, we could, of course, find its derivative. But, all right, so this says, given an equation, if you have two initial conditions, one involving the function, one involving the derivative, you are guaranteed to get an answer. So the last theorem said, if you can find answers, you can build an infinite number of answers. And this one now says, we promise you that you can find answers. So eventually we're going to get to the point where we say, here's how we find all the answers. And that'll be our important thing. All right, so to build up to that, we need another definition. Two functions defined on an open interval are said to be linearly independent on I, provided that neither is a constant multiple of the other. So let me give you some examples. F of x equals 6x squared. G of x equals 12x squared. Are those linearly independent?
Yes.
No, those are linearly dependent. These are not linearly independent. Because I can take the first one, I can multiply it by something, a number, and I can get the second one. In fact, what number do I multiply the first one by? 2. So these are not linearly independent. These are linearly dependent.
That's because they're scalar multiples?
They are scalar multiples of each other. If I take 2 and multiply it by f of x, I get g of x. So those are linearly dependent. How about the functions f of x equals 6x and g of x equals 12x squared? Are those linearly independent? No?
They are linearly independent.
They are linearly independent. Oh, we have dissension.
I don't know why though. I just feel very
If I start with this function, what do I have to multiply this function by to get that function? 2x. Is 2x a constant?
No, it is not.
No, it is not. So are these linearly independent?
Yeah.
Yes, because I cannot take this one, multiply it by a number, and get that one. Those are linearly independent. All right. Definition of the Wronskian, named after another famous dead mathematician. Let f and g be any two functions. The Wronskian of f and g is defined to be the Wronskian of f comma g is. What does this symbol mean? Anybody know? This is a matrix, but normally when we write a matrix, we write it with brackets that look like that.
absolute value.
It's not absolute value. If this were just a number, then that symbol means absolute value.
You don't do that.
Anybody know what this symbol means when you're dealing with matrices? This symbol is called determinant.
Yeah.
Oh, yeah.
So this could also be written as determinant of the Wronskian. And if you're dealing with a 2 by 2 matrix, what's this determinant? Anybody know how to figure that out?
Yeah, it'd be the f times g prime minus f prime times g.
You multiply diagonally this way, so you're going to have f times g prime. And then you're going to subtract and you multiply the other way. G times f prime. It looks an awful lot like something, except that something that I'm thinking of would have a plus in the middle. It looks an awful lot like a product rule, doesn't it? Leave one alone, take the derivative of the other, then leave the other one alone, take the derivative of the first, except the product rule would have a plus in the middle. Yeah, this is the determinant. And determinants of matrices tell you many, many things about the matrices. Have you guys gotten to determinants yet in linear algebra?
No.
No, you will.
Kramer's rule of physics.
You did Kramer's rule in physics, which uses determinants.
Yeah.
Yes, absolutely. Kramer's rule is a pretty good way for solving systems of equations, especially if you have like 3 by 3 or 4 by 4 equations, and you're allowed to use a calculator to find those determinants. Kramer's rule is a very good way to solve. All right, so here's where Wronskians come into play. Suppose that y1 and y2 are two solutions to a homogeneous second-order differential equation on the interval on which p and q are continuous. If y1 and y2 are linearly dependent, then the Wronskian will be 0. If y1 and y2 are linearly independent, then the Wronskian will not be 0. All right, so I have a question for you. Are f of x equals sine x and g of x equal cosine x linearly independent?
So how do you determine whether something's linearly dependent or independent?
Well, there are two ways. Sometimes you can just look at them and you can tell. That's what we had before. When I give you 6x squared and 12x squared, you could very easily tell that I could take this one, multiply it by 2, and I got that one. The second way you do it is you use the Wronskian.
So when you're dependent means it like, what does it mean? Like, does that mean like?
So the question I'm asking you is, can I take sine, multiply it by a number, and get cosine?
Okay.
That's what linearly dependent means. Linearly dependent would mean I can do that. Linearly independent, that's the important one. Linearly independent means no matter what number I multiply sine by, I'm never going to get cosine. So the way we normally tell is we take, for functions we're not sure about, we take the Wronskian. So the Wronskian says you write down your functions, that's sine x and cosine x. Then write down your derivatives. What's the derivative of sine? Cosine, what's the derivative of cosine? Negative sine. And then you take the determinant, which looks like an absolute value symbol, but it's not. When you're dealing with a matrix, that symbol stands for determinant. The determinant says you multiply diagonally. What's sine times negative sine? Negative sine squared x. Minus, there's always a minus in the middle, you multiply the other diagonal. Cosine squared x. Simplify that. What do you get when you simplify that? You factor out the negative 1, then you have sine squared plus cosine squared, but sine squared plus cosine squared is 1, so that's the number negative 1. Which does not equal 0. So that tells us that these are linearly independent.
Could you have said that because they're not scalar multiples, that they're linearly independent?
Yeah,
But if
But-
we weren't 100% sure about that, we use the rent.
correct.
Okay.
So we're going to be dealing with functions there where it won't be easy to just look at them by inspection and tell are they linearly independent or not.
Okay.
So to make sure, we will compute the Wronskian.
Okay.
Okay? Questions on that? All right, so we're getting to the important theorems here. These are the ones we really need. Corollary. What's a corollary? Or Jay would pronounce it corollary, but that's okay. What's a corollary?
Something that's correlated.
No. A corollary is a little fact that comes immediately from the last fact that you talked about. So that's called a corollary to a theorem. So this corollary says every homogeneous second-order linear equation has two linearly independent solutions.
Okay.
Sounds good.
So, this theorem says if you start with a second-order differential equation, you're guaranteed that you can find two different solutions. Before, we had a theorem that says we guarantee you can find one solution. This one now guarantees you can find two solutions. If you have a second-order differential equation, how many solutions do you think there are?
3.
Well, when we had a first-order differential equation, how many answers were there?
Well, one? No.
On the test that I passed back, problem number 2, for example, was a first-order differential equation. How many correct answers were there to problem number 2?
One.
There was one correct answer. Problem number 3 was a first-order differential equation. How many correct answers were there to problem number 3? There was one correct answer. We now have second-order differential equations. How many correct answers do you think there are?
2.
There are 2 correct answers. If we had a third-order differential equation, how many correct answers would there be? 3. All right, so there's a pattern there. So this is a very important thing. This says if we have a second-order equation, we can be guaranteed to find two different solutions. Well, we assumed that, but now we actually know it for sure.
Right.
George, is there a trivial solution? Or
There could be a trivial solution. Y equals 0 could be a trivial
would that
solution.
be one of the two? That wouldn't be an addition to the two, right? Or an addition to the one?
Well, notice here, we are absolutely positively guaranteeing that neither of these solutions are the trivial solution. Because notice this one, the y value is 1 at one point. And this one says, well, here the y value is 0, but our derivative is positive, which tells us somewhere else our y value cannot be 0, correct? Because the graph has to be increasing.
Yeah.
So this is saying we guarantee two non-trivial solutions even. So it's even better. So remember that theorem we had way back at the beginning. What did we have once we had two solutions? Once we had two solutions, we had a third one, didn't we? And we had an infinite number of solutions. And so here's the big theorem, theorem number 4. The big theorem, theorem number 4 says, given any two linearly independent solutions of a homogeneous second-order linear equation, there are real numbers C1 and C2 such that any other solution can be written as a linear combination of the first two. In other words, in simple words, this says, once you find two answers, you found them all. That's what this says in simple terms. But what that does not do is tell us how to find the answers, does it? No, it does not. Leaves us hanging. All right, so how do we find them? Solve. Now we're going to say, how do we solve the second order differential equation y double prime minus 4y prime plus 3y equals 0? Well, I don't know what the answer is, but from experience, from the first chapter, I saw that an awful lot of the time, our equations had solutions that had e's in them, didn't they? If you go back and look at the test that you just took, every single differential equation had an e in it somewhere eventually. So I'm going to guess, I don't know if this is the right answer or not, I'm going to guess that my differential equation has a solution that looks like that. And I'm going to take this, I'm going to take its derivative, I'm going to take its second derivative, I'm going to plug it in and see if I can figure out what the number r would have to be. See if I can get lucky. All right, so what's the derivative? Y prime is r e to the rx. And y double prime is r squared e to the rx. All right, so I'm going to plug that in. I get r squared e to the rx minus 4r e to the rx plus 3 e to the rx equals 0.
Kind of like the homogeneous substitution.
Similar to like the homogeneous substitution, yep. Except it's going to work out so much better. You're going to like this so much. What do you do next? How do you solve that equation?
Pull out an e to the r.
Pull out an e to the rx. You have e to the rx times r squared minus 4r plus 3 equals 0.
Oh my god, yeah.
When does e to the rx equal 0?
Really negative.
When
So the answer is, well, when r goes to negative infinity,
Yeah.
but I want r to be a number. So what number can I plug in there to get 0?
0.
Now if I plug in 0, I get e to the 0, which is 1.
Oh.
I'll give you a hint. It's a trick question.
You can.
I can't. No matter what number I plug in for r, I'm never going to get 0 there.
Yeah.
So I can't get 0 from there. I have to get 0 from here.
So we have to split up the
Oh, so you-
r squared
that
plus
equals
4r plus 3. Just factor that.
You don't have to.
So those are the 0. One of those parts on
r squared minus 4r plus 3 happens to factor as r minus 3, r minus 1.
Yeah.
So it's 3.
So I get r equals 3 and r equals 1. How many answers did I get? 2. So my two answers are y1 is e to the 3x and y2 is e to the 1x. So I just discovered 2 solutions.
I like this.
Are those solutions linearly independent?
That's where you have to use the Wronski.
You can use the Wronskian to check. These 2 solutions are indeed linearly independent. So according to that theorem we had a few minutes ago, once I find 2 linearly independent solutions, what do I have?
All
I have all of these solutions. So the general solution to this equation is y equals some constant, I'll call it c1, e to the 3x, plus some other constant, I'll call it c2, e to the x.
So we don't have to find the constant. We just have to find y1 and y2.
If I gave you initial conditions,
Okay.
you would plug in the initial conditions to find the 2 constants,
And then leave it alone after that.
and then leave it alone. All right, so here's the big question. We started with a second order differential equation. Where was the calculus involved to solve this second order differential equation? There was some.
taking derivatives.
We had to take these derivatives and plug them in.
Yeah.
But notice what's going to happen. Look at this equation we ended up with right here. Look at this piece.
Oh, that was
Yeah, it's like basic.
It's quadratic. Not only is it quadratic, where did the negative 4 and the 3 come from? It came from that negative 4 and that 3 right there, didn't it? So how do you solve second order differential equations?
You just back to.
All you have to do is be able to solve that quadratic equation. All right, so this is called the characteristic equation. So if you have y double prime plus py prime plus qy equals 0, r squared plus pr plus q equals 0 is called the characteristic. I don't know. I can't spell characteristic. Characteristic equation. If you can't spell it, you abbreviate it. See? Characteristic equation. In order to solve the second order differential equation, all you really need to do is be able to solve that characteristic equation, which is quadratic. Can you solve quadratic equations? Can you solve every quadratic equation?
Yes. Quadratic equation.
You can use the quadratic formula and you can solve every quadratic equation in the world, which tells you what?
We might have imaginary
Always
numbers.
have a solution.
You might have imaginary numbers. All right.
Which means we just stopped that problem.
So what happens when you have r? You have e to the r, where r is an imaginary number.
Take another math course.
We can't write that down. It's imaginary.
Come back after break. We'll discuss that. We will fix that problem. The other problem that we might have, what if I gave you this? What if I gave you, let's see, I got to think of one here. Y double prime minus 6y prime plus 9y equals 0. We set up our characteristic polynomial, our characteristic equation. It's r squared minus 6r plus 9 equals 0. And we solve that equation. Oh, yeah, not so happy now, are we? Because what are the solutions to that equation? There's only one solution with degree 2. We get r equals 3. So we have one answer. One answer is y1 equals e to the 3x. How many answers do I need? 2. No, I need 2 non-trivial solutions. So where's the second solution?
R 3 plus I.
No, no complex numbers.
Could be negative 3, no?
Negative 3? You could try e to the negative 3x, plug it in, it won't work. You can try it, it won't work.
One?
Good guess.
No, one won't work.
The second linearly independent solution, and you can either trust me, or you can take some first derivative, second derivative, and plug them in. The second linearly independent solution will be x e to the 3x.
No, mine is that.
Why is that? First off, it would be pretty easy to show that these two functions are linearly independent. Can I take this first function, multiply it by a number, and get the second function? No, I had to multiply it by x, so they're clearly linearly independent. The thing that would be a little bit harder, but not too bad, is to take the first derivative, take the second derivative, plug them in, and show that it works. And you can either go home and do that, or you can trust me. Those are your options.
If we get one,
One
so we
number
can
is
usually
the
just put
argument.
an x in front of.
So if your characteristic polynomial only gives you one solution, the second solution is multiply by x, always.
Awesome.
Always. So the general solution to this equation would be y equals c1 e to the 3x plus c2x e to the 3x.